Today we're going to talk about Chapter 4.1, Exponential Functions. We'll talk about how to evaluate and graph exponential functions, evaluate functions with base e, and use compound interest formulas. So the definition of an exponential function is defined by f of x is equal to b raised to the x power, or y is equal to b raised to the x power. B is a positive constant other than 1, so that means b is greater than 0 and not equal to 1, and x is any real number. So let's talk about how to evaluate an exponential function. The exponential function f of x is equal to 42.2 times 1.56 raised to the x power models the average amount spent, f of x in dollars, at a shopping mall after x hours. What is the average amount spent to the nearest dollar after 3 hours at a shopping mall? So x represents the number of hours, and we're looking at 3 hours shopping at the mall. So I'm going to plug in 3 into the function. Whenever I see an x, I'm going to put in a 3. Now you can type this into your calculator all at once. So here's my calculator. It's 42.2 parentheses 1.56 raised to the third power. And you get 160.2. So we're just going to round that down to 160. Okay, so after 3 hours at a shopping mall, the average amount spent is $160. So now let's talk about the domain of f of x is equal to b to the x power consists of all real numbers from negative infinity to infinity, and the range consists of all positive real numbers 0 to infinity. The graph passes through the point 0, 1, and that's because anytime you raise a number to the 0 power, you get 1. The y-intercept is 1. There is no x-intercept. The graph of the exponential function goes up to the right and is increasing. The greater the value of b, the steeper the increase. The graph, if b is in between 0 and 1, the graph goes down to the right and is a decreasing function. The smaller the value of b, the steeper the decrease. This function is a one-to-one and has an inverse that is a function. As the function approaches but does not touch the x-axis. So it approaches the x-axis, but it never touches the x-axis. So y equal to 0, or the x-axis, is what you call a horizontal asymptote. So we're going to talk about some transformations. So I gave you the table for the transformations and which way they shift up or down, left or right. So this is my base graph. F of x is equal to 3 to the x power. If you were to make a table to get these points, let's say I put in -2, -1, 0, and 1. We get 3 to the -2 is equal to 1/9. We get 3 to the -1, which is 1/3. 3 to the 0 power is 1, and 3 to the first power is 3. Okay, so those are the points that I graph. So you have a point here, the point here. Remember, the graph always passes through the point 0, 1, and then you got the point 1, 3. This is 0, 1, and then it's going to be hard for me to type this in here. Let's see, -2, 1/9, and then this point here is -1, 1/3. Okay, and then as I stated, the horizontal asymptote is the x-axis. So I'm going to put a dotted line here. Okay. All right. So on your homework, it's going to ask you to do a horizontal. It's going to ask you to graph it and do the horizontal asymptote. So in this graph, this is x minus 1, 3 to the x minus 1. This is a horizontal shift. Okay, so you're going to shift 1 to the right. So what you do is you're going to add 1 to each of the x coordinates. Okay, so remember when we had our table, this is 3 to the x minus 1. So the these values stay the same. Oops, this is 1. This is 3. So remember we had 1, sorry, we had -2, we had -1, 0, 1. So I'm going to add 1 to each one of these. You get -2, you get 0, you get 1, you get 2. So, no, I wrote that wrong. Hold on. This is -1. I'm going to erase this too. Okay, this is -1. -1, 0, 1, 2. So these are the points that you're going to graph. So all you're doing is shifting the x values 1 to the right. So this is the graph here. Okay. Once again, the horizontal asymptote is the x-axis. It's also y equal to 0. Okay, for this next one, you have 3 to the x power minus 1. This is a vertical shift. You're going to shift 1 unit down. Okay. And since you shifted 1 unit down, this is going to be your horizontal asymptote is also going to be 1 unit down. So this is y is equal to -1. Okay. This next one is -3 to the x power. This is a reflection about the x-axis. Okay, so this is the horizontal asymptote. As you can see, the graph flips about the x-axis. Okay, and this next graph is 3 to the -x. This is a reflection about the y-axis. Okay, once again, the horizontal asymptote is the x-axis. And then this last graph, -3 raised to the -x, this is a reflection about the x and y-axis. Okay, once again, horizontal asymptote is the x-axis. All right, so now we're going to talk about the natural base e. The number e is defined as the value that is 1 plus 1 over n to the nth power as it approaches as n gets larger and larger. So as n goes to infinity, the approximate value of e to 9 decimal places is e equal to, or approximately equal to, 2.718281827. Okay, we usually just round it to 2.72. You also have an e button on your calculator, so you don't have to worry about typing in this long number. All right, so let's look at this problem. It says the exponential function f of x is equal to $1,145 e raised to the 0.0325x models the gray wolf population of the western Great Lakes f of x years after 1978. We're going to project the gray wolf's population in the recovery area in 2017. So remember, x is the number of years after 1978. So in this case, we're looking at 2017. We're going to subtract 1978 away from 2017 and we get 39. So I'm going to put 39 in for x. Okay, so this is going to be, and we're going to type this into our calculator all at once. So, like I said, you have an E button here. I don't know if you can see it on this screen, but it's right above the LN button. So if you hit second LN, this E will pop up. And then you can type in the exponent. But let's go ahead and write this in. We have 1145. I'm going to hit second LN, and then I'm going to type in this exponent, 0.0325 times 39. And as you can see, this is all written as an exponent. And when I hit equal, I get 4066.99. I'm going to go ahead and round that. 4066.99, which is approximately 4067. So this indicates that the gray wolf population in the western Great Lakes in the year 2017 is projected to be approximately 4,067 wolves. Now let's look at this next problem. The bar graph shows the percentage of U.S. high school seniors who applied to more than 3 colleges for selected years after 1980 through 2013. Okay, so I got each year on the as the bar and the percentage of high schoolers who applied to more than 3 colleges. So it looks like it's increasing. So this data can be modeled by f of x is equal to x plus 31 and g of x is equal to 32.7 times e raised to the 0.0217x. F of x and g of x represent the percentage of high school seniors who applied to more than 3 colleges x years after 1980. So this first model that you see is a linear model. That's the f of x. The g of x is your exponential model. So you have 2 different models. Okay, so according to the linear model, what percentage of high school seniors applied to more than 3 colleges in 2013? So remember, x represents the number of years after 1980. So in this case, we're going to take 1980 and subtract it from 2013, and that's 33 years. So I'm going to plug 33 back into the linear model. And when I get that, I get 64. So in this case, it's 64%. Okay, so according to the linear model, 64% of high school seniors applied to more than 3 colleges in 2013. In the exponential model, I'm going to plug it in, and you can type this into your calculator. I just showed you how to do it. When I do it here, I get 66.9, or you can just say 67%. Okay? So the question is, what function is a better model for the data? Is it the exponential model or the linear model? Well, based on the bar graph in 2013, it was 69%. So it looks like the exponential model is a better model because it's closer to what the bar graph shows us. The bar graph shows us 69 for 2013. Okay. All right, so now this is a you try problem, so I'm going to have you try this on your own. Um, I'll go ahead and put the I'll go ahead and put the answers in here for you. So this is f of 30, which is 61%. This is g of 30, which is 63%. And then the answer here is the linear model. All right, the next part we're going to talk about compound interest. After T years, the balance A in an account with principal P and the annual interest rate R in decimal form is given by the formula. A is equal to P times 1 plus R over N raised to the N times T power. N represents the number of compounding periods per year. So I gave you this table. So if your problem says semi-annually, it's compounding 2 times a year. Quarterly is 4, monthly is 12, daily is 365. If you have continuous compounding, it's A equal to P times E raised to the RT power. So let's look at this first problem. We got a sum of 10,000 is invested at an annual rate of 8%. Find the balance in the account after 5 years subject to quarterly compound. So let's write out what we have. The principal amount is 10,000 at a rate of 8%. We're going to change that to a decimal. T is 5 years and is compounded quarterly. And we're trying to figure out what A is. So we're going to plug everything back into this formula. This is 1,000. 1 plus 0.08 all over 4 raised to the 4 times 5 power. So what I did was I did the stuff in parentheses first. And I got 1.02 raised to the 20th power. And then when I calculated it out, I got 14859.47. So that's how much money you should have in the account after 4 years. Sorry, 5 years. If it's compound continuously, we're going to use this formula here. So this is 10,000 e to the 0.08 times 5. You get $14,918.25. Okay, this is a you try problem. I'll go ahead and put the answers in and you can try this on your own. Okay. This one is 13157.04 and the last one is 13165.31. There we go. All right, so that's the end of this lecture.